The special properties of water. This is one of those things that we have talked about in all of our science classes, I believe. Definitely biology, physical science a little bit, and yet again in chemistry. So I hope I'm trying to kind of do this in a little bit different way, but I don't know. We'll see. So, water. I have listed out all of the especially cool things that water can do. So, some little tiny bugs can walk on water. We know that our blood, which is mostly water, is able to flow through our capillaries. Our capillaries are the little tiny blood vessels, so little tiny tubes, very small diameter. Think of them as straws, but smaller, like teeny tiny straws. We can dissolve lots and lots and lots of things. We can dissolve things that are very acidic. We can dissolve things that are very basic. Soaps dissolve in water. All sorts of salts can dissolve in water. The list goes on and on and on. One of the only things that doesn't dissolve in water would be the lipids or the oils and fats. They're kind of the exception, but almost everything else dissolves to some degree in water. The ocean temperature, and I chose the Pacific Ocean. I did some Google. The temperature of the Pacific Ocean is fairly constant. It ranges from 60 to 65 degrees Celsius, so 5 degrees fluctuation, and that's pretty crazy given the extreme temperatures that the atmosphere kind of endures. And as we know, ice floats. Yes, the solid form is less dense than the liquid form, and that is not true for anything else. Solid is less dense than the liquid. The opposite is true for every other substance that there is. So again, special property of water. And this is kind of like your fun fact for the day. Water occurs naturally as a solid, a liquid, and a gas on Earth. Okay, right? We have solid, big ice caps, icebergs, solid ice, floating in the ocean. Here's my ocean. Iceberg, we have liquid as the ocean, and then we have a gas, which is the clouds. The water vapor makes up the clouds. So solid, liquid, and the gas naturally on Earth all at the same time. And that's only true for water. Crazy. Okay, we are going to focus on some of these a little bit more so than others. We are going to talk about ice floating. We are going to talk about bugs walking on water, blood flowing through our capillaries. Those are going to be our main focal points for this chapter. And the because behind all of these is the hydrogen bond. I said bond, not bomb. hydrogen bond is the reason why water can do all of these crazy things. The hydrogen bond, our definition is, it is a strong force from a hydrogen that is bonded to a very electronegative element. Electronegative, this is one of those words we had a while back, is the ability to attract electrons to itself. So something that is a really, really strong or big, like electron hog, a bully that pulls electrons to itself. For the hydrogen bond purposes, there's only 3 atoms that meet that criteria. It has to be a fluorine, an oxygen, or a nitrogen. So those are the only 3 very electronegative elements that will work to form the hydrogen bond. So I've always remembered them as phone, F-O-N, phone, fluorine, oxygen, and nitrogen. If you look on the periodic table, they're actually in the other order, nitrogen, oxygen, and fluorine, but anyway, that's how I remember it. So we have to have a hydrogen, and it has to be bonded to a very electronegative atom. A hydrogen bond is fairly weak. It cannot hold a molecule together, but it can form an attraction between molecules. So a hydrogen bond would be a very, very, very weak bond. It will not hold a whole molecule together, but it will cause molecules to attract each other, which creates a polar molecule. So we've talked polarity before. Polarity is the uneven distribution of charge and water is polar. We have drawn this picture before. We've discussed the regions of charge with a water molecule. There are 2 pairs of unshared electrons on a water molecule. Oxygen here is our very electronegative atom, and so the 2 electrons that are forming the oxygen-hydrogen covalent bond are shifted more to the oxygen than they are the hydrogen. So now apparently I'm going to make my electrons purple, which means there's a whole lot of negative electrons on the oxygen side of the water, and that leaves a positive charge from the hydrogens on the other side. So we can kind of draw a dotted line down the water molecule to indicate its negative, partially negative side and the partially positive side, which only plays to the fact that water is polar. And because it's polar, it forms hydrogen bonds. Over here in my mix of hydrogens, or my mix of water molecules, I'm going to show the hydrogen bonds, and they are going to be formed from a hydrogen to an oxygen of neighboring water molecules. And one water molecule will actually be bonded, hydrogen bonded, to 4 other water molecules. And so I don't know if I have this laid out exactly perfect. but I tried. Again, an oxygen will form 2 hydrogen bonds from it because it's got 2 unshared pairs of electrons, so each of those is capable of forming a hydrogen bond. But like I said, I don't know if I have it drawn out exactly right. I tried to make this, I tried to set it up, but it looks like some of them are a little close together. Because like I want to do this, like right here, but that won't happen. 1 hydrogen will not form 2 hydrogen bonds. So that's not gonna work out. But that's okay. I feel like you kind of see where this is going, because this is not the first time I've drawn this out for you, but it's been a while, so I wanted to show it to you again. Hydrogen bond there. Let's see if, I can maybe turn, sorry guys. I want to see if I can kind of find an area. So this will work. If I look at this water molecule, you can see that it's got hydrogen bonds formed to 4 other, sorry again, that one wouldn't. This water has 4 hydrogen bonds to 4 neighboring water molecules. So maybe I should have just quit there, but that's okay. Okay, you get the point, I think, I hope. So what that does is it pushes the water molecules farther apart than what they normally would be, and that creates little pockets of empty space. And that is why ice floats. It's why the solid form is less dense than the liquid form, because this is empty space. So it pushes them farther apart. The polarity factor, along with hydrogen bonding, is a great explanation of these 2 things. Bugs walking on water is a perfect example of what we know as surface tension. And this is where water molecules at the surface, so all of these that would be up along the edge, are more strongly attracted to each other, creating what kind of looks like a skin on top of the water. So surface tension is a vocabulary word, so we're going to squeeze in the definition. Surface tension is the apparent elasticity of the surface. And this is primarily due to water molecules being attracted to other water molecules, which is known as cohesion. Water molecules attracted to other water molecules. Water attracted to water, specifically molecules at the surface, which is why we say surface tension. But there's our explanation for why bugs can walk on water. And then we have blood flowing through our capillaries, and this is known as capillary rise. And it would occur anytime we have a tube with a small diameter, like our capillaries, but also would apply to a straw. Whenever you put a straw in your pop or something, it automatically pulls up that pop because pop's mostly water. Capillary rise is vocabulary. So the rise of a liquid in a tube with a small diameter. And this is primarily due to adhesion. Adhesion is water molecules sticking or being attracted to other surfaces, such as the plastic in the straw or something like that. Adhesion is why water runs down the side of your glass when you're trying to pour it into another glass. Instead of like pouring out like it should, it just like slides down the side of your glass and like, makes a mess. That's adhesion. And I think we have surface tension, which is cohesion, capillary rise, adhesion, hydrogen bond, polarity. Drew some pictures. Okay, I think we've got it.